Okay. A very good morning to all of you, and welcome to Let's Talk Astronomy. I welcome all of you on behalf of the Let's Talk Astronomy team. Um, we are all aware that the entire world right now is trying to adjust to the new normal. Good morning to all of you, and welcome to Let's Talk Astronomy. Sorry for that. Okay. Yeah. So we are all aware that the entire world is now trying to adapt and adjust to the new normal way of living, staying at home, which has enforced us to stay at home because of the COVID-19 pandemic. These challenging times should not stop us from learning something new to kindle our scientific and engineering knowledge. Therefore, some of us who work in different fields of astronomy and astrophysics have got together, and we want to try to engage the Indian student community to discuss with us about astronomy and share their experience. In this session, we are going to give a broad overview of astronomy and discuss the challenges involved in it. Towards the end of the session, we also plan to give you career options and how to become an astronomer. Okay. So our team consists of PhD students and postdoctoral researchers from all over the world. They're being displayed over here, and the places where they work in and the different universities where they are studying at right now. So there are a few points that we would like to emphasize on before starting these sessions, just to make it easy for you guys to ask questions and discuss with us. So these talks are broadly tailored to address the 9th to 12th standard students. And based on how your internet connectivity is, you might experience a little bit of a lag with the audio and the video. So try to follow us carefully. And if you have any questions, you can ask us as follows. So if you go to the Let's Talk Astronomy web page, you can see that there is a section where you can click on how to ask a question. So you can either click over there, or you can go to the description section in your YouTube video, and you can click on the hyperlink which is being given over there, and it takes you to a web page where you can ask your questions. So you can type in your name, you can type in your email address, and you can ask the questions based on which category it belongs to. A daytime if it belongs to the sun, and nighttime if it belongs to the stars, and career if it's related to career. You can also give us comments and feedback. I'll give you the outline of the session. So we will be starting off with the daytime astronomy, and then we will be having a 10-minute session for the question and answers. And then we will have the nighttime astronomy session, and then again a 10-minute session for the question and answers. Then we will give you an overview of the career options in astronomy and how to go about pursuing astronomy as your career and future prospects of it. And then there will be a broader question and answer session. In this question and answer session, you can ask questions related to the daytime astronomy, related to the nighttime astronomy, as well as a career. So this is specifically meant to answer all those questions. And just like the way I showed before, you'll have to type in your questions over here. So if it's a daytime astronomy related question, you'll have to key in your question here. If it's a nighttime astronomy question, you'll have to key it here. And if it's a career related astronomy question, you'll have to key it there. And please do not forget to click on the submit button. If you do not click on the submit button, we will not be receiving the question and we will not be able to answer. And due to time constraints, we might not be able to answer all the questions right away, but we will surely get back to you. And please do keep checking our webpage for the FAQs and all the question and answers that has been asked and answered. So without further ado, let me hand over the screen to my colleague who's going to talk about the sun. Sajal, it's all yours. Sajal, you can start sharing right now.
Good morning. Welcome everyone to the first session. As Mohan informed that this session is about daytime astronomy. So when we asked to fill the form for this our program, so most of the time you people asked like a lot of fascinating questions about the galaxy, about the exoplanet, and etc. But we have seen nothing much about the sun. So we decided let's inform you in this individual session about our nearest star, the sun. So before I proceed, I would like to tell you if you have any questions specifically to the particular slide. So while asking the questions, you just write down the slide number, which is given in that below here. So then we can come back to you and we can try to answer you. So why do we need to study the sun? So we live in the solar neighborhood. So it has influence on our like a life starting from what we eat, and this is the reason for our existence. So this sun provides us energy which sustain the lives on the earth, and it has many influence, like it has influence on the seasons, it has influence on the harvest, and even the sleeping pattern of all living creature on the earth. And there are billions of stars in our galaxy Milky Way, and sun is one of them. And being the closest star is around 150 million kilometer away from us. If we study the sun, then it is a gateway to understand the other star in our galaxy. So, and our sun is very dynamic, and could it be dangerous? So yeah, it may be dangerous to us. So let's try to understand that how it can affect us and what impact it can have on us in this talk. So let's start by seeing the structure of the sun. The sun has multiple layer of structure like a onion. So it this every layers is different from the other, and it has important aspect to produce energy and transferring energy to the different layers and finally to the space. So starting from the center part of the sun we call as a core, and this core region the temperature is around 15 million Kelvin. So when I tell about that temperature 15 million Kelvin, so it doesn't makes much sense, it's like a huge number. So let's compare this number some familiar stuff which we know. So we know our average human body temperature which is around 310 Kelvin, that means 37 degrees centigrade. Okay, another example I can give you. So this molten lava which is coming out from the volcanic eruption which has temperature around 1000 to 1500 Kelvin. Now you compare the temperature of the core of the sun which is around 15 million Kelvin. That means the sun is very hot. What we can't even imagine how hot it is. So what is happening there to make this core of the sun is very hot? So in the core of the sun, what is happening in three different processes, that four hydrogen nuclei fuses them together and to form a helium nuclei. The mass of the individual helium nuclei is little less in combination of four mass of the hydrogen. So this less mass, who is that extra mass, what is happening, it is converting to the electromagnetic energy in the form of gamma ray photon. And this gamma ray photon from the core, it moves to the different layer. So now you keep on the eye on the temperature of the every layer of the sun. I believe that you'll be surprised by that number when I'm talking about this. Okay, so the energy from the core of the sun as a gamma ray photon is moves to the next layer, and it radiates, it radiates. So that's why this zone is called radiation zone. It's similar like in winter we put a fire, and to get the heat we just sit surround it, right? and and this energy or heat transfer from this fire, it comes to us by radiation. So similar process also is happening here. So this zone, from the from top of the core to the outer layer of the radiation zone, this temperature drops around 15 million Kelvin to 2 million Kelvin. And next layer of the sun we call as a convection zone. What is happening here? Here hot plasma is boils up and bubbles up, and it goes to the surface of the sun, and it is released the heat to the space and come back to the down. So it is similar like a when you boiling the pot of water. So similar process also is happening here. So the base of the convection zone, the temperature is around 2 million Kelvin, but in the surface of the sun the temperature is around 5700 Kelvin. And this is the outer layer of the solar interior. But we cannot see all this interior structure of the sun because sun became very opaque. So what we can see, only visible surface of the sun, which is called as a photosphere. And this photo means light. That means from that surface the light escape from the sun, and the temperature around 5700 Kelvin in this. So when you see the photosphere from far, it become very sharp. But when you go close to very close to the photosphere, so what you can see is some grains like structure, and these are the structure it comes because of the convection pattern. So this structure we call as a granulations. And recently we have a very good telescope. It's a 4-meter class world largest telescope called Dikist, and with that we have recorded the solar surface, and you can see here how granule patterns are evolving with time. And this individual granular pattern is around 700 to 1000 kilometers. So if you compare like one of the state of India like a Madhya Pradesh or Gujarat, so this is the similar structure, similar like size of this structure. So the outer layer of the sun we call as a chromosphere and corona, but we do not see them. Why we don't see them? Suppose in your house, so there is a bright bulb is there. So in front of that, if you put a small candle light, do we see the light coming from the candle light? No, right? So it is a very faint source for us. So the similarly the photosphere of the sun is so bright that we do not see the faint light coming from the chromosphere and corona. So there is a natural phenomena like a total during total solar eclipse. So this moon covers the solar disk, and so the bright region is getting covered, then chromosphere and corona is getting visible to us. So in this way we can study the chromosphere and corona. So the first outer layer is called chromosphere, which extended up to 2000 to 5000 kilometer. And in this region, the temperatures rises from 4000 Kelvin to 8000 Kelvin. And next extended part of the solar atmosphere is called corona, which can extend beyond the interplanetary region, and the temperature is around 1 to 20 million Kelvin, and this is only visible during the solar eclipse. So we have one example. that in 2017 there is a total solar eclipse where moon completely covers the solar disk, and you can see the extended corona, and you can see there's a lot of structure. It's like this corona is very structured. So while I am giving the internal structure of the sun, so did you notice that there are so many other structures also on the sun? You can see there is some dark spot we call as a sunspot, and some bright region we call as a flare, and some structure which is hanging from the sun we call as a prominence. So, and I have told you to keep an eye on the temperature. In the photosphere of the sun, the temperature is around 5700 Kelvin. But when we move away from the sun, in the chromosphere, the temperature is around 4000, it increased to 8000 Kelvin. And the corona, the temperature becomes like a 1 to 20 million Kelvin. So what is happening? So suppose when we put like a fire and we sit beside that, we get more heat, right? And when we go away from the fire, we experience less heat. So but in this case, what we are seeing that when we move away from the sun like a photosphere to corona, the temperature is increasing. So to understand this, all this aspect of the sun, what is happening, what could it happen, so we have to study in better way what is happening on the sun, right? So let's try to understand. So the sun is a gas of ionized plasma. So there, in that ionized plasma, there is a lot of electrons, charged particles which are moving, right? Those moving charged particles, what is doing in return, it is making like a sun as a huge magnet. So this average magnetic of the field, the average magnetic field of the sun is around 1 Gauss, but in the localized region, this magnetic field strength is around 1000 to 4000 Gauss. So when I'm telling this number, it doesn't mean to anything to you. But let's compare something. So we know Earth has a magnetic field, right? Due to the motion of the iron core. So average magnetic field of the Earth is around 0.5 Gauss. So now you see the number, how the localized strong magnetic field exists on the sun. So it is around 1000 to 4000 Gauss. I can give another example. So when we do some laboratory experiment with a bar magnet, so which has a magnetic field strength around 100 Gauss. So now you can see there is a huge concentrated magnetic field present on the sun. This sun is a ball of ionized gas, right? So it rotates. So when it rotates, so this equatorial part, it moves faster than the polar region. Due to this magnetic field gets winds up, and because of that, it may form knots or some king kind of stuff. And due to the buoyancy, when this magnetic field come emerge to the surface, what we see as a result, the strong magnetic concentrated region, and which is called as a sunspot, and which appears as a dark because it has a very strong magnetic field. It does not allow the bottom layer to heat up, so it has a temperature little cooler than the surrounding, so it appears as a dark spot. And the size of the sunspot is so huge that it is almost comparable size to the earth, and sometimes it become even bigger, and which can be similar size of our like a biggest planet in our solar system, Jupiter. So this magnetic field does not just limit to the photosphere and from the sunspot. It can extend to the even further region. So, and this sunspot, whatever we are seeing here, it does not always remain constant on that photosphere, and it changes over time. So some year you can see that number of sunspot on the sun is very less. Sometimes it is increasing, like a lot of numbers you can see, lot of sunspot on the sun you can see, and it follows like 11-year cycle. And this magnetic field strength does not limit on only on the photosphere, it extends to the further outer layer of the sun like a chromosphere. So you can see in the chromosphere, what we can see, this magnetic structure as a like a dark thread like structure. It's a long structure which appears as a dark, is called filament. And similar structure when you see in the limb side, so you can see as a bright prominent structure, and these are like a magnetic structure. And these magnetic structures are not stable. Sometimes it's like a stretch to the outer layer. It's just like a rubber band. When it is stretched to the outer layer, and it cannot sustain after some time, then it breaks. So it breaks. So when it breaks, what is happening, there will be a large amount of eruption, and it is associated with lot of energy released. And when this kind of eruption happen, you can see lot of charged particles are expelled to the space. So this kind of phenomena is called coronal mass ejection. So during this flare, lot of energy is released, which is around 10 to 20 to 20 to 25 joules. So now if you compare how much is the solar energy expelled during this kind of event, so it is almost like a millions of 100 megaton hydrogen bombs. So now you can imagine how big and huge amount of energy is getting released during solar flare. So how does it matter for us? So when this kind of eruption happen and lot of energetic particles are expelled to the space, so it can move in any direction, right? So and it can comes to even our earth direction. When it moves towards the earth, so it interacts with that our earth magnetic field, and this charged particle, it can trapped in that magnetic field and reach to the earth atmosphere through the polar region. So when it enter to the polar region, it can interact with that earth atmosphere, like with nitrogen, oxygen, or water molecule, and it produce like a beautiful this kind of northern light, like a polar lights is called aurora, which can be seen from north pole or south pole. So apart from these natural phenomena, we have another impact. So it this kind of big solar eruption or coronal mass ejection, it can influence our space in many ways, because nowadays we are using so many satellite communication, right? When these charged particles come to the space and towards the earth, so it can disrupt that satellite communication, it can disrupt the power grids. So what will happen, our cell phone may not work, our TV may not work. And during this eruption time, if some astronaut happen to be in the space, so his or her life can be in danger also. So it has many way it can impact us. So can we do something about it? Yes, if we study properly what is happening on the sun and when this kind of eruption may occur, so then we can predict this kind of phenomena, and then we can save ourselves to get this kind of damage. So how do you do that? So how do you learn all this? Okay, before going to this section, I can tell you, never ever look at the sun directly, because it is very intense and it will burn our retina, then you may go blind. So even during the eclipse, you should not look at the sun. So how you have to look at the sun? So you can use the solar filter always. And to study the sun in better way, we require like a multi-wavelength observation of the sun. So when I'm talking about the multi-wavelength, how do we do? So suppose one of our hands or leg got broken, so, and we went to the doctor. So doctor first, to check this, what he does, he take an x-ray, right? When we took an x-ray of our body parts, what we can see the information about our bone, so where it can get break, right? So when, so then x-ray give the information our internal body structure like bones. But when we take a picture in the visible wavelength, what we can see the skin. So this is the picture of a Richard Feynman. And similar way, if you take a picture in infrared, we can see how energy is distributed, like a heat energy is distributed over the whole photograph. And in this picture, you can see this person is holding a bottle, which is little colder than his body temperature. That's why it is appearing as a dark. So in the similar way, if you observe the sun in different wavelengths, then you can see different structure present on the sun and what is the phenomena is happening on the sun. So how do you do? So when this kind of like a white light pass through a disperser like a prism, it sprays the light in different color like a VIBGYOR you have studied already, right? So in the natural phenomena we can see as a rainbow. So this is the example of the solar spectra in visible wavelength. But sun emits radiation from X-ray to radio wavelength. So when you want to observe the sun from the ground, we cannot observe in all wavelengths. So like a gamma ray, X-ray, and ultraviolet, it is getting blocked by the earth atmosphere. Only we can observe the sun from the ground through like a visible wavelength or corona or radio wavelength. Or if you want to observe the sun in x-ray or ultraviolet, so we have to send a satellite or telescope in the space. So here is the example when we observe the sun in multi-wavelength, what we can see. So when we are observing the sun in continuum wavelength, what we see, there is a dark spot on that, it's called sunspot. And when you go like a different wavelength region, like a UV and X-ray, what we can see, different structure present on the sun, like a loop, some bright region, and many more things. So this multi-wavelength observation of sun help us to understand individual structure on the sun present. So how do you do that? So there are so many international solar missions are there to observe the sun. So recently in this year, in February, the solar orbiter has been sent to the space, and which will go very close to the sun, and it has a unique trajectory. It will first ever give image of the sun of the polar region. So with this we can study the inner layer of the sun, and even the heliosphere, what is happening on this. And there is a world largest telescope, is a 4-meter class telescope called DKIST, and it is started operating from last year December. And with this also you can study like a multi-wavelength study of the sun. And following this, there are several space mission has been sent to the space to study like a chromosphere and corona, or like energetic events what is happening on the sun, like a Parker solar probe, solar dynamic observatory, Hinode and RESI, all those things. So here I'll mention some solar observational facility in India. So starting from in Udaipur Solar Observatory, it is in Rajasthan. Their telescope called MAS is, the full name is Multi-Application Solar Telescope. The purpose of this telescope to study the sun in optical and like a photosphere and chromosphere region of the sun. And there is another telescope also is there in this observatory. It's called GONG. And the southern part of India in Gauri Bidanur, there is a radio telescope. It's a long antenna of arrays. So this with this telescope, we can study the corona of the sun. And there is another observatory in Kodaikanal Solar Observatory, which is operated by Indian Institute of Astrophysics. And this observatory is situated in that beautiful Palani range of southern uh, mountain area. And this is very old observatory. It was uh, established in 1899, and so all this old Madras observatory's facility was transferred to this observatory. And in this observatory there are several telescopes are there, and very recently installed telescope called H alpha telescope. With that we can study the chromosphere of the sun. And there is a worm telescope. With this we can monitor that active region or sunspot on the sun, and many more things we can do. There are several telescopes present in this observatory. And in this observatory, one very nice thing is that from 1904, we have observed the sun in different wavelength, and all data has been stored. So you can do a lot of fascinating stuff about the sun, many more research thing we can do. And here one example of the image of the sun is taken in 1928. And you can see there are some sunspot present in this image. And if you have interest, if you want to see how this 100 years old data looks like, you can go through these slides, go through this link, and you can see. And I'd like to end the presentation by the last slide. So we are very exciting about that Indian space observatory is called Aditya L1. This will be the Indian first solar mission, and which is going to be launched in the next year. And this space observatory has like a 7 payloads, and with this we can do like a multi-wavelength study of the sun, the chromosphere and corona we can study. And this observatory is going to be placed in the Lagrangian point L1. So in this region, this gravitational pull by the sun and earth is almost same, and it is opposite direction. So we don't need any extra fuel to keep the observatory there for long. So if you want to be part of this facility and explore more about the sun, so wait for our session on career guidance. Thank you. If you have any question, please send the question as Mohan explained the Q&A link, which we have sent to your email. So we'll try to answer this. Thank you.
So, thank you, Sajal, for a very nice talk. And we have got few questions, but we still ask the students, if you want to ask more questions related to the talk, please fill up the Q&A page. And we will be taking few questions that we have already received. So we received one question from Mohan, which is, how do sunspots form? And Supriya would be taking this.
Yeah, hi. That's a very nice question. So, like Sajal was mentioning in his talk, uh, there are magnetic fields on the sun, mainly because of the kind of particles sun is made of. So these magnetic fields, because of something we call differential rotation, which he also showed in his slide, uh, are twisted over a period of time. What is this differential rotation? Because the sun is not a solid object, it is made of like the plasma, or imagine like a big ball of gas. So the center of the sun rotates in a much faster way as compared to the poles of the sun. So because of this, the magnetic fields are eventually twisted, and because of this twisting they get concentrated in small blob like region, and these blobs are what we see as sunspots. Sunspots are basically very concentrated region of magnetic fields. So that's how they are formed. Okay.
Thank you, Supriya. Now we have another question from Pahel. Uh, what is Gauss? This is for Soumya.
Hi, Pahel. Yeah, it's an interesting, you have made a nice observation. There is a system which gives us definitions of different units. For example, if you are talking about weights, you express in terms of how many kilograms it weighs, or distance, for example, is expressed in terms of meters. So there is one system which defines this set of units, and it is called a CGS system, which stands for centimeter gram second. And in that system, Gauss is a unit which basically measures how strong a given magnetic field is. So this unit is derived from a German mathematician and physicist by name Carl Friedrich Gauss, and he did extensive work on measuring the magnetic field of Earth. So in that honor, so this unit is named as Gauss. So Gauss is basically a measure of how strong a magnetic field is in a given object.
Thank you, Soumya. Now we have one question from Nishkan. Can we harness the entire energy of the sun by building a Dyson sphere or similar structures? What are the challenges around it? Mohan would be taking this.
That's a nice question. There's a nice video on this by Kurt Kazar on YouTube. So to see what are the challenges that we will be facing, we'll have to first become a type 1 civilization. And we are not yet there. We are still trying to send man to the moon or man to the Mars. Even that hasn't become a continuous affair. So once we make that a regular process, then we can think of harnessing the energy of our star, first partially and then entirely by building a Dyson sphere. So we are still not there yet, and we still don't know what are the challenges, because we don't know how long can man sustain while doing these interplanetary travel and stuff like that. So we are still heading towards that.
Thank you, Mohan. We have another question from Roshan. This is for Supriya. So the temperature of photosphere is 5700 Kelvin, but the temperature of the chromosphere starts from 4000 Kelvin. So why is there the decrease in the temperature?
Yeah, that's a very nice observation from the presentation Sajal gave. Thank you. So basically, as you saw when Sajal was talking, the temperature as we start from the core where the energy is produced, it starts from around 15 million Kelvin, and it eventually reduces as we move from layer to layer. By the time you reach photosphere, yeah, like you said, it's around 5700 Kelvin. But chromosphere is the next layer. It's merely because of the further transport of radiation and its interaction with the particles present in the solar atmosphere. It collides and interacts with them, loses some energy, and moves further. Because of this, you start seeing the decrease in temperature. At the same time, you have to notice that after a certain point in chromosphere, when you move further away in the solar atmosphere, it starts increasing. This is the interesting phenomena that happens on the sun. This heating, the further heating that happens on the solar atmosphere, is purely because of the magnetic field activity that is happening on the sun.
Thank you, Supriya. We have another question from Visual from Mohan. Are stellar engines possible to build?
I would again like to refer you to another video by Kurt Kazard. So there are many theories put forward, and there is one put forward recently where they taken the energy from the star and propel it in one direction, and hence propelling the star and the entire solar system in the other direction. So I would recommend you to watch that video on Kurt Kazard, because they have explained it beautifully with nice graphics. And yeah, if that is true, then yes, of course, stellar engines are possible to be built.
Thank you, Mohan. We have one question from Archana for Sandeep. What are neutrinos?
Sandeep, you have to unmute.
Okay, meanwhile, we can take another question from Kirtana. This is for Krishna. How is the prominence created?
Hi. So that's a nice question, Kirtana. So prominences are basically very cold plasma suspended in the atmosphere of the sun. So we at the moment know that they are formed by so-called catastrophic cooling, which is basically the heating rate is slower than the way it is cooled down. So it radiates faster the energy and then it cools down faster. So it is colder and denser. This plasma is suspended in the atmosphere by the magnetic fields. That's how prominences are formed. Yeah.
Thank you, Krishna. Sandeep, would you like to answer? What are neutrinos?
Yeah. So neutrinos are the particles which are formed when neutrons are converted to protons, or there are many flavors of the neutrinos. So it can be electron type neutrino, proton type neutrino, or tau neutrino, and so these are the particles which are having very less mass, and they are scattered very less when they travel. So that they can provide very important information about the sun. And apart from sun, various other sources in faraway universe. Yeah.
Okay. Thank you, Sandeep. We have one question for Rahul. How do we measure the magnetic field in the sun?
Hello, can you hear me?
Yes, we can hear you.
Okay, so this question is from Pehal. Pehal, your question is, how do we measure magnetic field in the sun? So actually, one thing that we do not measure, we infer magnetic field from the sun. Okay, for that we have instruments like spectropolarimeters, and generally using spectropolarimeters, we record Stokes parameters. So maybe you may be aware of Stokes parameters, Stokes IQV. So we generally measure linear and circular polarizations, and using these information, we infer magnetic field on the sun. Okay.
Thank you, Rahul. We have one question for Lokesh for Mohan. How do you find out about the different layers of the sun?
That's a nice question. So this also answers one of the questions, like how do we find the layers of the Earth? So the internal layers of the sun are found through something called helioseismology, which is similar to the seismology that earthquakes that happen on the Earth. Similarly, there are quakes that happen on the sun, and using them we find the internal layer, which is the convection zone. And we know that the sun has the core because of the uh, I'm sorry, I just lost it. Because of the nuclear fusion that happens, we start getting neutrinos, and through this we know that the core has a particular. And the solar atmosphere is found by observing it in different layers, like how Sajal and others pointed out. The atmosphere is at different temperatures, and at different temperature you have emission or absorption from different elements. So based on this, you get to see different layers of the atmosphere. Sajal, in fact, showed a image of it, like how different in different wavelengths you can actually see the different depths on the sun. So using radiation and using helioseismology, we get to know the interior and the atmosphere of the sun, the different layers.
Thank you, Mohan. One final question before we move on to the next session. This is from Achyut for Sajal. What are the main functions of RESI, the NASA mission?
This RESI mission was mainly designed to study the solar flare. So mostly during the flare, what are the high energy particles are coming out or it is released. To study this mission was like a sent. So mainly we study that high energy particles which is coming out during the solar flares. So this is the main aim of this facility.
Okay, I think we have time for one more question. So this is from Sri Vishnu for Soumya. What is the SI form of Gauss?
Yeah. So, like I said earlier, similar to CGS system, there is another system called the International System of Units, and you can convert units from one system to the other. So in CGS, magnetic field is measured in units of Gauss, and in the International System of Units, which is called the SI system, you measure it in terms of Tesla. So 1 Tesla is basically 10,000 Gauss.
Okay, Samir, thank you very much. So now we will be moving for the talks from nighttime astronomy sessions. So moving to Preeti.
Good morning, everyone. So I'm sure you had a great session on our nearest star, the sun. This session will focus on the part of the sky that is visible to us once the sun sets, the other half of the day, the night. So we have 3 topics planned for you in this session: stars, galaxies, and planets, cosmology, and instrumentation. So let's start with our first topic, stars, galaxies, and planets. We are going to go on a journey from our seats to the edge of the universe as we know it. And we are going to do it in 10 minutes. So hang on to your seats and brace yourself for a journey much faster than the speed of light. Before we get started, let's have a quick look at how we are going to cover this distance of 46 billion light years in 10 minutes, a distance that light itself takes 46 billion years to travel through. Now, in our everyday life, we are used to measurements that are linear in nature. like using a ruler or an inch tape, or when you add ingredients while cooking. In a linear scale, the difference between any two consecutive numbers remains the same. So for example, if you see here, second row minus the first row, 2 minus 1 is the same as 3 minus 2 is same as 4 minus 3. While a linear scale is the most basic form of representing data, it becomes very difficult to represent very large numbers on a linear scale, especially in a subject like astronomy. So we instead use what's called a non-linear scale. In this scale, the difference between two consecutive numbers increases drastically. It is not a constant like in the linear scale, but the ratio between two consecutive numbers remains the same. So in this case, 10 minus 1 is not the same as 100 minus 10, is not the same as 1000 minus 100. But if you do 10 by 1 is the same as 100 by 10, is the same as 1000 by 100. In this particular example, this is a logarithmic scale. The numbers increase so fast that I could not even fit the last example on the slide, the Mount Everest. You would have seen this type of scale being used a lot in the last few weeks to show the COVID-19 data. So if you observe the y-axis, you see that they don't increase linearly like 100, 200, 300, 400, and so on. Instead, they go up logarithmically from 100 to 1000 to 10,000. So now let's go to the edge of the universe on a logarithmic distance scale. We are going to start from our home base, our Earth. The 10 to the power 17 here refers to the diameter of Earth in meters, which is nothing but just 10 followed by 7 zeros. Now we are going to take a step forward in the logarithmic scale from here, and we are going to reach the edge of the universe. So let's start. So our first step on the logarithmic scale brings us to 10 to the power 8. We are simply multiplying the number by 10 at every step. At this step, the diameter of that circle is 10 times bigger than the last step. So we went from a circle that fit one Earth inside it now to a circle which can fit 10 Earths along its diameter. In the next step, we will reach a circle of size that can fit 100 Earths inside it along its diameter. So let's continue. Now about 1/3 way in, you will come across the moon. That is the farthest distance into the universe that humans have gone so far. As we reach 10 to the power 9 meters, we easily cover Earth, Moon, and Moon's orbit around Earth. At this distance, we can now fit 100 Earths along the diameter of that circle. Next step. So 10 power 10 meters, a small part of the Earth's orbit itself comes into view now. Next step, 10 to the power 11 meters. That circle has now extended to also include a part of Venus and Mars's orbits around the sun. Let's keep going. Next step, 10 to the power 12 meters. We now have the 4 inner rocky planets, Mercury, Venus, Earth, Mars, along with their entire orbits, and also the asteroid belt inside it. How far do you think the next step is going to take us? Maybe to Jupiter's orbit, or maybe we will reach as far as Saturn? Let's see. 10 to the power 13 meters. At 10 power 13 meters, we have reached the edge of our solar system. The outer limit of our solar system is defined by the Kuiper belt. It is a comet-rich area of our solar system that lies just outside Neptune's orbit. Keep in mind, Pluto is not defined as a planet anymore. Just a little outside this region is the farthest any man-made spacecraft has reached. That is Voyager 1, which was launched in 1977. Let's keep going. 10 to the power 14 meters. At 10 power 14, we are now leaving the entire solar system behind. Next step, 10 to the power 15 meters. You don't see the solar system anymore. You just see the sun as a star in the sky filled with other similar stars. If I had shown this image to you directly, you might have never known that our entire existence is around that star at the center of the image. Let's keep going. Next step, 10 to the power 16 meters. We left our solar system when it was 10 to the power 13. It has taken us 3 steps on the logarithmic scale to finally reach our nearest star to our solar system, Alpha Centauri. You've probably heard of it before. Alpha Centauri is actually a star system which consists of 3 stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Now, just as we zoomed out from our sun, what do you think might happen? if we zoom into a different star, like the Alpha Centauri system, you will likely see that they have a solar system of planets around them as well. These are called exoplanets. Exo means outside. So planets outside our solar system are called exoplanets. It is now believed that most stars have planets around them. In fact, astronomers have recently calculated that there are at least 8.8 billion stars with Earth-like habitable planets around them just in the Milky Way galaxy, just in our galaxy. 8.8 billion stars with Earth-like planets. That is more planets than the number of people on Earth. That's a huge number. Let's get back to our journey. We are now going to 10 to the power 17 meters. Until now, if you had noticed, the background stars seemed very still. Now we have finally come so far that even the background stars have started to move. 10 to the power 18 meters. We have reached what is called the solar neighborhood. It is just a predefined distance from the sun that contains all our neighboring stars. Next step, 10 to the power 19 meters. You now start to see a lot of haziness in the image, not just stars anymore. This is the interstellar medium. Now, as the name suggests, interstellar medium, it refers to the medium that exists between stars. This is outer space, the region that we typically consider to be vacuum. It is not a perfect vacuum. It contains a lot of gas and dust molecules in it, and that's called the interstellar medium. Next step, 10 to the power 20 meters. At this distance, you see some sort of a structure develop now. It's not just a little bit of haziness or cloudiness in the image anymore. There's a definite structure to this. That is an arm of the Milky Way galaxy. If you're not familiar with what that is, you'll see in the next image. Next, go to the next step, 10 to the power 21. So at 10 to the power 21, we reach the Milky Way galaxy itself. Now, the Milky Way is a spiral-shaped galaxy with arms made of the interstellar medium. So the collection of these gas molecules and dust molecules forms the arms of the Milky Way. Now, our galaxy contains between 100 to 400 billion stars. And the sun is located on one of these spiral arms as shown in this image. What does our Milky Way contain though? What all does it have in it? Now, it has a wide range of stars, which we are aware of. Okay, it has a lot of stars of different colors that you see in the night sky. So this particular plot over here is a plot of the brightness of a star as a function of its temperature. So those alphabets that you see on the x-axis, O, B, A, F, G, K, M, are just different categories of stars based on their temperatures. That blinking spot that you see above G, above 5,500 Kelvin temperature, that is where our sun is right now. That is the current brightness of the sun and the temperature of our sun. And this is how our sun will move on this graph from its birth to its death. So it's halfway through its life at this point. And if we know the initial mass of any star, then we can predict how that particular star will move on in this graph. Then we have multiple star systems like the Alpha Centauri system that you saw a few slides back. Most stars have their own planets, and those planets have their own moons, which are called exoplanets and exomoons. We also have different types of nebulae, which are just very dense regions of the interstellar medium. Now, a nebula can be a region where either new stars are born or a region where a star died with an explosion spreading out all its matter. Then there are globular clusters, which are collections of stars very tightly bound by gravity. Then you have open clusters, which are collections of stars which are more loosely bound by gravity. Both of these types of clusters are good targets for binocular viewing. And of course, the most famous supermassive black hole at the center of our galaxy. Now let's go back to our journey. So that was our 10 to the power 21 meter. Now, almost everything you see when you look up at the night sky is inside that 10 to the power 21 meter circle. Within that circle you see right now, except for maybe 2 or 3 nearby galaxies, which are visible in the night sky. Everything else that you see when you look up is within that circle over there. Let's go to the next step, 10 to the power 22 meters. So you saw those little fuzzy objects near Milky Way on the left side. We have now left our galaxy behind, and those two small fudges that you saw are the satellite galaxies of our galaxy. They're called the Small Magellanic Cloud and the Large Magellanic Cloud, and they're visible to the naked eye from the southern hemisphere on Earth. So 10 part 23 meters. We have now reached a distance so far that even the galaxies now appear as a single dot in space. So every dot that you see on the screen right now is an entire galaxy, which itself contains billions of stars. Now, if we zoomed back on one of these galaxies, instead of going back to our Milky Way, we turn a little bit and zoom into some other galaxy. What do you think you would see there? You would see the same. You would again see stars and planets and clusters and nebulae, whatever we find within our own galaxy, the black holes, etc. Now, these galaxies also can be of different types. So this is a morphological classification scheme for galaxies, which was invented by Edwin Hubble. So that would be a name that you would have heard of, for example, the Hubble's telescope. And morphological simply means that the galaxies are classified based on their visual appearance. And our Milky Way falls in the bottom of this fork with spiral arms. Let's continue. We have now reached 10 to the power 24 meters. You don't see much happening here. Every dot that you see there is just another galaxy. Next step. 10 to the power 25 meters. At this distance, we start to see the galaxies grouping together to sort of form little clusters and superclusters of galaxies, whose sizes are huge in the orders of a few billion meters. Next step. 10 to the power 26 meters. We have now reached the limit of the observable universe. So if you remember, the moon was the farthest any human has ever been. The edge of the solar system was the farthest any man-made spacecraft has reached. The circle that covered the entire Milky Way was everything that the human eye has ever seen. And this is the limit up to which we can look into the universe using instruments that we have. We don't yet know what is beyond this limit. This is called the observable universe. So we have now reached the point in space and time for cosmology to take over. So thank you.
Now that we have come to the edge of the observable universe, I think it is time for us to understand the origin and evolution of the universe as a whole. This study is called cosmology. Now, it turns out the universe is homogeneous and isotropic. That is, it is the same everywhere and in all directions. So, in case you were in a ego bubble,
Hello. Yeah, we'll start about the cosmology part. So, Preeti, can you share the screen?
Yes.
So till now we have seen the observable universe from our solar system to the very large scale to the what you say is the cosmic web, where you have galaxies of clusters of galaxies. Now in this session we would like to go further to the origin of universe And yeah, let's see how much we know. So, okay, I think, yeah. Can you go one slide back? Yeah. Yeah. So in this slide, you see that our universe is a homogeneous. Homogeneous mean to say is like, if you see, if you go around the space, and you will find that more or over the structures are similar. Like the overall behavior of the structures is similar. So as you can see in the this below left panel, you can see that there is like a big kind of pattern, which pattern is same, and it is also isotropic. The mean is that if you go in any of the direction from the point, it will look similar. So our universe overall, it has a property, it is homogeneous as well as isotropic. And then in 1929, Hubble made a very peculiar observation, and that was really very interesting in the sense that our universe is expanding. He observed the galaxies which are far, which are having a distance from us, and he observed one important thing is the galaxies which are very far away from us, they are moving very fast, and which are closer to us relatively, they are moving slower. So that was a nice observation in the sense like it changed our view that our universe is expanding, and that can be really explained with the Olbers paradox, which says like if our universe would have been static, then we would have seen that all the sky should have been brightening because of the light of all the stars, but it is not the way. So our universe is moving. Then only we can say that, or it is expanding. Then only we can say that we see dark sky is a night. Okay. So can we go to next slide? Yeah. So our universe is made of what are the constituent of our universe. So whatever visible universe we see, it is made of only 4.6%, which we call as baryonic matter. And all this matter makes galaxies, stars, and planets, and which whatever we see around us. And so there is something else which we cannot detect, and it is made of, that is called dark matter. That is 22% of the universe is made of dark matter, and this first prediction was made in the galaxies from the rotation curves of these galaxies, which you see in the right panel of this slide. So it was done first by Vera Rubin in 1970s, and this was also a new understanding to our universe. And then there is a 73% content which we don't know anything, which we just can feel from the expansion of universe, that there is something called dark energy. And so we see that, so we don't know most of the stuff how the universe is made of. So can we go to next slide? So as we know, like how universe begin, we need to see about, like, as universe expand. So universe is thought to form from a big bang, and as universe expands, its volume increases and its density decreases and temperature decreases, and further on the energy per unit volume decreases. That is kind of thermodynamical system which we are aware of. So in the first few 1/30th of second, we saw that universe, there was a big explosion, and then universe took a very big inflation, in the sense like it became 36 times in 10 is about 36 time in fractions of second, 10 is over minus 32 seconds. So it was like a kind of a big inflation at a time, and after that there were nuclear fusion reactions happen, and then you have particles started to form, and then when the electron and proton start to interact, then when electron proton started interacted with the light, and that was the last time when the cosmic microwave backgrounds were released. And after that time, there was no interaction between electron and proton, and that was the dark ages. And after that, it ended up to some time. It continued to till some time, around 3 lakh, 30 lakh years. And then there was a again interaction started when universe was expanded such that it can they can interact each other. The photons and the baryons can interact with each other, and they started forming stars and galaxies, which we see now. And it has slowly evolved to the stage which we see today. And today we have all the planets, galaxies, and stars, which are looking homogeneous and isotropic, as we discussed in the previous slide. And we can go to next slide. So yeah. So this is a short video of how this cosmic microwave, which we see as the origin of all the structures we see around us. These were the small perturbation in the beginning of the universe. And as slowly universe expanded, this structure grew larger and larger with the effect of gravity. And we see the stars started forming. And these are first star. And then slowly structures evolved. And these are the cosmic web, which have evolved quite a lot. And now we can see that each point is the galaxy in this state. And then you have clusters of galaxies and superclusters and so on. Yeah, so next. So we can see, so there are many missions which are seeing the large scale structures in the universe. And there is a Euclid mission which will be seeing the structures in the very far away, which are very far away from us. We will be seeing the visible matter. And if we know the visible matter from their dynamics, we can get information about the what is invisible matter, which is dark matter. And from their motion, we can predict dark energy models, which theoreticians are building. And then in the right hand side, we have a Planck mission, which is which was sent by ESO, and it gave a very nice information about the cosmic microwave background radiation. And it was a really providing insight for the beginning of the universe. And because of this, we know a lot about the beginning of our universe. And below we have our square kilometer array, which will be detecting the presence of hydrogen atom in the universe. As you know, that hydrogen atom is the most abundant atom in the universe, and it releases kind of radiation which we call 21 centimeter radiation. They can travel very far, and we can get tremendous information about the first stars which are formed in the very early universe at the time when CMB was released. So this is a very powerful tool, and still we are hoping that this will provide us very good information. And now we can go to next part of this session. Avinash will take over.
Hello, everyone. So I am working in instrumentation, and I work as a postdoctoral fellow in engineering at one of the largest observatories in the world in the island of Hawaii in US. To all the aspiring engineers out there, you have a huge role to play in the field of astronomy. Most of the discoveries mentioned so far has been made possible or validated with the help of cutting-edge engineering in the field of astronomy. So what do you mean by engineering in astronomy? Most of instrumentation and engineering in astronomy is about building a great lens. You might have learned about lenses in schools. So about building a great big lens to collect the faintest of light coming from millions of light years away, and combine that with a super sensitive camera to convert that light into pictures and other forms of data. So that's most of what astronomy is about. So as you can see here, you have a lens which is focusing all the light to a single location. Instead of lenses in most of astronomy, we use mirrors mirrors of various types to concentrate light into a focus, because the mirror does not sag under its own weight. So how far have we come in making cutting edge engineering to observe the universe? It all started with a very familiar name, Galileo Galilei, who you would have heard of in your textbooks a lot. So on the left side is the first telescope that he built, and he used his eyes as the sensors because there were no cameras, no CCDs, nothing. And he used his eyes as the sensors to copy what he saw and to draw the craters of the moon. So this is the result. This is probably the first magnified astronomical image that humans have ever taken. And then over the years, over the several centuries, people started building bigger telescopes with bigger mirrors to collect more light and focus them into photographic plates. So this came after the advent of photography. You might have seen your parents use photographic films with the cameras and developing photographic films. Nobody uses that anymore. But about from 20 to 200 years back, so this was the main way to collect photographs, collect light and make them into photographs. So what you see here is a negative of a photograph which is taken through a telescope, which an astronomer is checking for any changes throughout the time and for other data, other signs of what it is. So, and now we come to the cutting edge of engineering in astronomy today. About 30 years back, we humans sent a telescope to space so that we could see the stars without degradation of light by the Earth's atmosphere. So you must have heard of this telescope's name. It's called the Hubble Space Telescope. And most of the beautiful images that you see on the internet, like this one, was taken by the Hubble Space Telescope. And the immense clarity of the image is because of the ability that we can send telescopes to space, and we have very highly sensitive digital cameras to capture those images. But is astronomy all about pretty pictures? Is that all that there is? Not entirely. It's about how we use those images to discover new things about the universe. In this example, let's assume that there is a planet orbiting a star several light years away from the Earth. So even using the best telescopes on Earth today, we cannot directly see if there is a planet orbiting that star, especially if it's an Earth-sized planet. So we look for the signature of the planet in the way that the starlight behaves when looking through the telescopes. So while we are looking through the telescope, if we see a dip in the starlight for a very short instant, or it could be days, or it could be months, then we can assume that there is a planet orbiting around that star, and we can calculate how far it is from the star. Or when you split the light which is coming through the planet's atmosphere, say with a prism, you see that some colors are missing from the starlight, which are depicted by these black lines, which are getting absorbed by the planet. So these missing colors would correspond to light being absorbed by the gases in the planet's atmosphere. So this will help in the detection of water and other compounds which can show the presence of life like we have on planet Earth. For example, so this is the spectrum or the colors that we get if the sun's light were to pass through the Earth's atmosphere. And we can see that this part of the colors or this part of the spectrum is less than the other parts of the spectrum, which means, and these colors correspond to the absorption spectrum of water. So we look for these signatures in the light which is coming from stars outside of the solar system to understand what kind of materials are there in the planet's atmosphere and whether there is a possibility of life on those planets. So where do you want to be when you grow up? Do you want to build huge radio antennas, which could almost span half a kilometer, like the fast telescopes, which is used for looking at black holes or alien signals? Or you could be using supercomputers to combine the data from various telescopes. You might have seen this picture quite recently. This was captured by the Event Horizon Telescope collaboration. And this is the first ever image of a black hole. And this was captured with the help of lots of radio telescopes all around the world working in collaboration. Or do you want to build huge mirrors on mountaintop telescopes which can see back in time so far to the first galaxies ever formed in the universe? Or do you want to play with a lot of liquid nitrogen, since most of the cameras in infrared and visible astronomy is almost cooled to minus 200 degrees Celsius? So a lot of cool things to do here. And this is the final frontier. So if you want to do ultraviolet or X-ray astronomy, you have to go to space, because you can't do it on Earth, because ultraviolet and X-ray light does not reach the Earth's surface. They are absorbed by various parts of the Earth's atmosphere, including the ozone layer and the water vapor in the Earth's atmosphere. So you will be working with many weird high precision mirrors. Or you would be sending balloons to space. You could be working with satellites. And you can see all of these images which I show here are taken, are things which are built by scientists in India. So this is taken in the Indian Institute of Astrophysics, Bangalore, where they send UV balloons with cameras off to space to capture the UV light above the ozone layer. And here there are a bunch of scientists who are working on ultra sensitive cameras which were built for this satellite called the AstroSat, which you might have heard of in newspapers. So this was sent to space because we could not see those wavelengths or colors of light if you are in Earth. So what all do we do among ourselves, among all the astronomers who are present among us? So one of us works on concept of how we would combine the data coming in from a radio telescope in space with the data from Earth. One of us uses lasers on telescopes to reduce the effect of the Earth's atmosphere on starlight on ground-based telescopes. And we have another person who is designing techniques for the precise control of mirrors for huge telescopes. There is another person who is designing CubeSats for the sake of ultraviolet astronomy. And yet there is another person who is creating a 3D map of the night sky with very sophisticated optics, as we have seen. So where do you want to be? If you want to work with the coolest instruments on the planet, please come to astronomy. Thank you. And for questions, Q&A session, Prasanna will take over the session. And please use not the chat box, the link that we have given in the beginning of the session to ask your questions. Thank you very much.
Thank you, Avinash, Preeti, and Arun for a wonderful talk. So now we are moving to our next session, which is Q&A session on nighttime astronomy. So the first question is, what is speciality of 1 parsec and why is it 3.26 light years? What is the significance of it? And this will be answered by Shubham.
Yeah, hi. That's a good question. So a parsec is really a contraction of two words, which is parallax, and the other is second, which actually is short for arc second. So it's parallax arc second. Now, what is parallax? It's basically the apparent shift in the position of a nearby object when you look at it in terms of its position on a distant background. So, for example, if you've noticed when you travel in a train or on a highway, the nearby objects like the nearby fields and the poles and the light poles and stuff like that, which is nearby, zooms past very fast. Whereas the distant objects, like if there is a mountain in the distance, it pretty much stays in the same spot. So that's essentially what parallax is. It's the change in the apparent position of nearby objects when viewed in the background of distant objects. And the same thing applies for the night sky. So when we look at nearby stars, they seem to move with respect to the distant background of stars when viewed from different positions. And so this effect is called a parallax, and it can be used to measure distances to nearby stars. And now the sun actually provides us with a natural baseline because, as you know, we are in orbit around the sun. So after 6 months from today, we are going to be on the other side of the sun, diametrically opposite, and roughly a distance of 300 million kilometers apart. And this provides an excellent baseline. So we can image the sky today and we can image it again after 6 months. And the nearby stars will seem to have shifted ever so slightly with respect to the distant background. And this can be used to measure distances of those nearby stars. And when you do that calculation, you can do a simple derivation for the expression for the distance. And so we measure that displacement in terms of angular distance, which you may be used to degrees, but in astronomy, the angles can be very small. So we break the degree down further, so we can break it into 60 parts and it becomes an arc minute, which is 1/60th of a degree. You can further break the arc minute into 60 parts and that becomes an arc second, which is 1/3600 of a degree. And so, so the parallax, so the parsec is essentially the distance at which a star will produce a parallax of 1 arc second. And that turns out to be roughly 3.2 light years.
Thank you, Shubham, for the wonderful answer. So next question is by Vijwal Singh. And question is it possible to create wormholes or they are naturally created? So this question will be answered by Prashant.
Yeah. Can you hear me?
Yeah.
Yeah. So wormholes are speculative objects in our universe. We don't know if they exist yet, or we don't know how to create one. What wormholes are two regions of space-time or in our universe which are connected in some sense. So these regions could be at very large distances from each other, but you still have a connection between them. To visualize a wormhole, you might have seen the movie Interstellar, where they go through a wormhole from near Saturn and then they reach the region near a black hole almost instantly. These might not be really possible in reality, but we don't yet know because we haven't found a wormhole or we don't know how to create one. Yeah, so that's about it. Thank you.
Thank you, Prashant. So the next question is from Roshan, and the question is, can you explain about Chandrasekhar limit? And this will be answered by Arun.
Hello.
Yeah, Arun, go ahead.
Yeah. So essentially, whenever a star is alive, there are two forces which are balancing each other. You have your thermonuclear pressure, which is pushing it outwards, and you have your gravitational pressure, which is pulling it in. So as long as balance is alive, the star is stable. It's in something called the main sequence. Now, once the fuel runs out, for smaller stars, especially like in the case of the sun, when the fuel runs out, what will happen is the gravitational pressure eventually takes over and it keeps collapsing further and further. But it cannot collapse into nothingness. There will be a force which is opposing this, that is given by an idea in particle physics where you cannot have multiple electrons in the same state. So this is called the electron degeneracy pressure. So when this electron degeneracy pressure balances your gravitational pressure, the star sort of stabilizes. The limit at which this happens, the maximum limit of mass where this can happen, is the Chandrasekhar limit, which is roughly about 1.4 times the mass of our sun.
Thanks, Arun. So next question is by Nirmiti, and the question is any planet or solar body visible in daytime under favorable conditions? And this will be answered by Avinash.
Hi, Nirmiti. Very good question. So yes, we can actually observe bodies in our solar system during the day. And you know, the sky during the daytime is like lit because of the sunlight scattered by our atmosphere. But during the night, there is no sun, so that we can see so many stars. So to start with, I would like to say that you can observe some objects which are very bright in the day sky. And the first object you want to start with is the sun, and definitely you can see that. And then you would have definitely seen the moon is also visible in the day sky. Due to its close proximity to the earth and its brightness, we can actually observe this. And you can also, in fact, see planets like the Venus. Currently, if you go out and see your evening sky, you will see the planet Venus hanging out somewhere 20 to 30 degrees above the horizon. But after a few months, maybe a month or two, give it a month or two, and you will start seeing Venus rising in the morning sky. So that's, you can call it the morning star. You would have heard that name before. And the same is with the planet Jupiter and Mars. Currently, we are in a position which is like, if you talk about the position of the Earth, the sun is in the opposite direction to Jupiter and Mars. So we see Jupiter and Mars in the night sky. But you have to wait out a few months maybe, and then when the the Earth goes to the other side of the sun, you can start seeing Jupiter and Mars in the night sky as well. For other planets, that's not possible because they're too faint to be observed from the Earth. So you possibly cannot see them. But you can also see some satellites like the ISS, which is bright enough. And in places where you have very clear skies, you can actually spot ISS. And in some cases, some really bright comets can also be observed during the morning sky. So I hope that answers your question.
Thanks, Avinash. So the next question is by Amritya, and the question is, how are auroras formed? And I'll answer this question. So as you know that our sun gives out heat and light, but that's not what sun gives out altogether. So sun also gives out charged particles. Now, when the charged particles travels towards Earth, this is Earth, and Earth is having its magnetic field around it, and it starts from the south side, which is the north magnetic pole, and these magnetic fields go around and kind of converge at the northern pole. So when the charged particles come in contact with the magnetic fields, they basically go in the helical path around these magnetic fields and come closer to Earth from north or south pole. And as these charged particles interact with the gases in our atmosphere, which is basically oxygen, nitrogen in majority, they produce lights, which is called as auroras. And there are two types of auroras we call, usually northern lights and southern lights, or aurora borealis and aurora australis. And these lights are usually visible in terms of green color or blue color. And the green color can be associated to the oxygen in our atmosphere, and blue and purple color can be associated with the nitrogen in our atmosphere. So basically, auroras are formed because of the charged particles coming from the sun, interacting with our interacting with our magnetic field, and further interacting with our gases in our atmosphere, and creating the ionized layers, and which basically emits back the aurora colors. So that's what aurora are. So the next question is by Nishkal Rao, and the question is a bit long. I'll just read out. Since the rate of expansion of universe is accelerating, what powers this expansion? Is dark energy just a hypothetical concept to fit things into this picture? Or is it anti-gravity which increases the rate of expansion? And this will be answered by Sandeep.
Yeah. So Nishkal, very good question. So yeah, our universe is accelerating, that we know from the current observation, which was one of them. One of course, is the Hubble's law, which says that universe is expanding, and then you have a supernova. There were observations of supernova which told that universe is accelerating, which was done in 90s, and they got Nobel Prize. And then so there is this model which is dark energy. It's a kind of a model which best fit to explain this expansion of universe. And I think this was introduced by Einstein, first introduced by Einstein himself, and then he said that it was his biggest mistake to introduce this constant, because it was very difficult to solve these equations. But as this thing progressed, and then we know that there are various models people are making, and it's just a model, but you cannot say it's a hypothetical model, because we know that universe is expanding given the fact, and then we have to do some modeling. So yeah, you need something, but we don't know anything about dark energy, what is its behavior, how it interacts or something. But we know that we need to put into the equation such that we can explain the expansion, and it is anti-gravity, yeah, because it is kind of against the gravity. So universe, there is a matter which will fall inside because of gravity, but this dark energy model by its nature, it's the anti-gravity. So yeah, it is kind of a negative pressure. So I hope this answered your question. Yeah.
Thank you, Sandeep, for the answer. And we'll take a final question. And you keep asking questions. We will take them in the end where we have a dedicated Q&A session. So keep asking your questions. So the final question of this session will be from Lochana. Is our solar system in a single plane? What about other solar systems? So this will be answered by Siddharth.
Okay, I'll answer that. So the fact that the whole of our solar system is mostly on one plane goes back to the initial stages of formation of the solar systems, and other solar systems as well. In the molecular clouds, when start forming, they have something called angular momentum, which is the inherent capacity or the inherent tendency of an object to rotate around an axis. It's like the spinning top. If you see a top spins about an axis, similarly, and so the top will retain that capacity to rotate unless friction acts upon it in real life situation. Similarly, in all these stellar systems where stars start forming in the clouds, so the solar system initially have some tendency to rotate about a particular system, which then means that all planets and all satellites around those planets and rotate about that initial axis of rotation and maintain that angular momentum. So that's why we would expect our solar system to have rotation in one plane. Other solar systems will also have their own plane of rotation, in which all the exoplanets of that solar system would rotate around. That is the expectation. But in some cases, like in our case, there are some planets and comets which do not exactly lie on that plane. That is often to do with collisions that happen during the formation of the solar system. In that case, there will be little obliqueness in the sum of orbits. But mostly in all solar systems, we'd expect one axis in which the whole solar system's planets would rotate. Yeah.
Thanks, Siddhartha. So we'll end this session here and we'll move to the career session, and Ramya will coordinate that.
Can you hear me?
Yes.
Yeah. So you all listen about the exciting talks in nighttime and daytime astronomy. So now I would like to tell you how you can be a part of this. That means if you want to have a career in astronomy, how do you go about it? So basically in astronomy, we have three different fields where each person can build their career. So one is theory simulation modeling, where you actually develop mathematical models, or you develop models based on some of the equations to understand some physical processes in the universe. The second one is observation and data analysis, where you observe the astronomical object and try to understand its characteristics. And the third one is instrumentation, where you build instruments or telescopes. Okay, I think my screen was not visible. I would start from the beginning. So you all listen to the exciting talks about daytime and nighttime astronomy. So I would like to give you an idea how to build a career in the astronomy. So basically, in astronomy, you can have your career in three different fields. That is, one is theory simulation modeling, where we develop mathematical models to understand various physical processes in the universe. Next is observations and data analysis, where you observe the astronomical objects and understand its characteristics. And the third one is instrumentation, where you build an instrument or the telescope to observe the sky. So these three are interrelated. Like if you are building up a theory based on your mathematical equations, you want to test the theory by observation and data analysis. And in order to obtain these observations, you need a telescope. So if you are interested in pursuing a career in one field, you would also know about the other fields. And if you are if you are planning to work in theory simulation or observation and data analysis, you should have a strong physics background. And if you want to work in building the instruments, then you have to have a good engineering background. So depending on that, you can come to astronomy, like you become a scientist or a professor, like with two different streams. One is you can have Bachelor of Science, where the major is physics, or Bachelors of Engineering, where you after this you can do Masters of Science, or which has also is a major in physics, and Masters of Technology. So in all these cases, once you finish your masters or bachelors, you can actually give an entrance exam, which is similar to your entrance exam which you give after your 12th standard, like NEET, or earlier you used to give AIEEE, IIT, JEE, etc. So one of this exam you can give after your masters or bachelors and join one of the research institutions in India to pursue your PhD in astronomy. And along with this, you can the individual research institutions also have their own exam, so you can give it, and you can get a good rank in that exam, and also join the research institute. So in India, the main two streams you can come into astronomy is, one is Bachelor of Science, that is BSc or MSc. Other one is Bachelors of Engineering. So if you want to do masters in astronomy before you go to your PhD level, then there are few universities which offer master's program in astronomy or astrophysics. You can Google these institutes. We'll put up the slides in our website, so you can get to know more information by Googling these institutes and then understand what is their entrance procedure. And after this, when you want to pursue PhD in astronomy, there are 8 dedicated institutes all over India which have a specific PhD program in astronomy and astrophysics. So these institutes have their own entrance test. Along with that, they also take entries depending upon nationalized entrance test. So there are 3 institutes in Bangalore, which is IISc, IA, and RRI, and one in Nainital, which is Aries. And there are 2 institutes in Pune, Ayuka and NCRA, and one in Mumbai, TIFR, and PRL in Ahmedabad. So you can get into any of these institutions for your PhD. If you couldn't get into any of those institutions, there are also multiple ISARs and IITs which offer PhD in astronomy. You can as well get in there and pursue your PhD program in astronomy. So this was a roadmap to pursue research in astronomy in India. But if you want to go abroad and pursue it, then you can actually, after your bachelor's, you can give an English proficiency test, that is IELTS for Europe and GRE or TOEFL for US. So you after this, you can go there and pursue your master's and also PhD. And one important thing is, during your PhD program, you don't have to pay any of the admission fees or any of the fees to any institute. You receive a stipend or a fellowship amount of about 32 to 35,000 per month in the case of India. And if it is abroad, you may receive about 1,000 to 2,000 USD. So before you decide to take up this research in astronomy, if you want to be sure, like whether I can do a PhD in astronomy or whether it is a good idea for me to go about it, then what you can do is, during your master's and bachelor's, you can attend some of the summer and winter schools conducted by these astronomy institutes, which I mentioned in my slides, where IAA, IUCA, these institutes conduct as summer and winter schools. You can attend it during your master's or bachelor's also. And also you can do an internship in these institutes, and also your 6-month project which you are supposed to do during your bachelor's and master's. And along with that, you can also attend the outreach events conducted by these institutes and interact with the PhD students and the faculty there before you take up your career in astronomy. So what are your job prospects? In the case of engineering, people who come up from bachelor's or master's of engineering, they can take up various technical jobs in institutes such as ISRO, IAA, IUCA, just before doing PhD. That means if you don't want to pursue PhD and you still want to be a part in astronomy or one of the big projects which are happening in astronomy, then you can apply for a job just after your bachelor's or master's. And even after PhD, if you don't want to pursue your career in research or academia, that means you don't want to become a scientist or you don't want to become a professor, you can also apply for a research-based jobs in the industries, where, because you will have the training in different optics, mechanical and electronics during your PhD. So depending upon that, you can also take up an industry job. So the other important aspect is, if you're not sure about career in astronomy, but you just want to continue it as a hobby, then what are the things you can do? There are various planetariums across India, for about 47 permanent planetariums which are present. So you can visit these planetariums, attend the Skywatch sessions and various talks which they conduct. Or you can join one of the astronomy clubs. Like you have various astronomy where there are many amateur astronomers who interact and would share very interesting things which are happening. So you can be part of those astronomy clubs, and you can also take part in national and international astronomy olympiads. And there are some cool projects about astronomy in zooniverse.org. You can just do it to have fun. And there are also like courses which are conducted for a small duration to give overall idea of astronomy, which is a REAP course or a 100-hour astronomy course, which you can attend and see if you are interested in astronomy further. So if you have any questions regarding the career, you can enter in the link which has been given to you, and we'll be happy to answer the questions.
Okay. So, okay, so let's begin with the Q&A session. For this session, the first question is by Bhuvneshwari, who wants to know what course can I take up in college to enter in the field of astronomy, and what are the job opportunities in astronomy? So Siddharth, you want to address that?
Yeah, I can try and answer that question. So as Ramesh said, there are multiple things that you can, multiple paths that you can do after 12th. Either you can do engineering or you can do go for physics, bachelor's in physics. So depending on these two, that it will decide, the answer will depend on that. So if you go for physics, I think you can just go for standard physics courses and do a bachelor's and do a master's, and then that should suffice in terms of preparation to take up a career in astronomy in itself by doing a PhD. But when you let's say you do engineering, and that is something that I did. I was a bachelor's in mechanical engineering, and then I did came for a PhD in astronomy. So then you can select some courses which are more suited towards, let's say, which has more physics content in it, like thermodynamics or fluid dynamics, which often get used in astronomy, for example. Or you can decide, choose to do electronics courses, which often get used in radio astronomy and gives you a flavor of how to detect, for example, radio signals from space. So the main answer, that's probably my answer. So if you go for physics after 12, then it's pretty straightforward in the sense that you don't have to do much deciding in what courses you take. You can basically take all courses, and that will prepare you in some sense for PhD. But if you go for engineering, then you can choose more physics oriented subjects and more related to electronics or antennas that will help you in terms of it can make you better prepared for taking up astronomy after your bachelor's in engineering or master's in engineering. Yeah.
Okay, thanks, Siddharth. The next question in the career section is by Charan, who wants to know what course I should take after 12th to become a cosmologist. So, Sandeep, you want to take that?
Yeah. So yeah, it's a very immediate question when you're in your school. Like whatever you want to become, you would like to know what immediate step you need to take. So yeah, for going into the field of cosmology, there are two ways. Either you can go into the hardcore theory side, or another is the thing you can go into the instrumentation side, where you both of these require different pathways. If you want to go into hardcore theory, then you need to be very good in the physics and mathematics. So you should be either go towards this BSc MSc path in a physics or mathematics if you want to be hardcore theorist. And if you want to go into the instrumentation side, if you want to build instrumentation to detect the observations which we discussed in the talk, like cosmic microwave radiations and last test structures and this hydrogen atom detection. So for this, you need a BTech kind of path, BTech, where you will learn the engineering part, how to build instrument, these kind of things. So these can be two ways where you can enter into the cosmology. Yeah, I hope this answers.
Thank you, Sandeep. The next question on the career section is by Pehel. Sorry. Okay, let's take the other one first. So this question is by Pranav, who wants to know what career is possible if I'm from the electronic and telecommunications engineering background. Avinash, can you take that question?
That's a good question, Pehel, but I hope my colleagues already would have given you a very good idea of how to go forward when you are an engineer and you want to pursue your career, but I'll just refresh it for you. So if you're a bachelor's of engineering in electronics, you have two primary ways to go. If you want to take over your interest in engineering and carry that over to astronomy, and you apply that in astronomical research, you can choose to do MTech in astronomical instrumentation and also continue with the PhD, or you can choose to pursue a pure science career, as Siddharth had pointed out. You can apply for these through GATE and JEST. There are like these two are the primary exams, and then there are some institutes which take their own entrance tests like DFR or I think INAT, and then there is IAST. So there are a few unique. You can give these exams and you can actually qualify for these institutes specifically if you want to pursue your career. So you have two ways. One is to just continue your interest in electronics and take it to astronomy, or you can choose a pure science path through applying for PhDs and integrated PhDs through all the institutes in India. So yeah, that's my answer. I hope that's clear for you.
Okay, thank you, Avinash. So this question is by Pehel. And the question is, what are the conditions to go in space? Avinash, Surendran, do you want to address that?
Hi. Yeah. So just a disclaimer, all of us here are astronomers. None of us are astronauts, first of all. And if you really want to be an astronaut as of now, so the only two countries who have sent humans to space are the United States of America and the former Soviet Union, which is now Russia. So unless you are citizens of those countries, it is very difficult to be an astronaut right now. But as you may very well know, India is starting its own astronaut program called the Gaganyaan. So every country which starts the astronaut program initially for the first 10 or 20 years will need mostly test pilots from the Indian Air Force, for example, from the Air Force of that country. So once the spacefaring program, human space program is well tested, I mean, making sure nobody dies in the process of going to space, everything is taken care of, then comes the scientists. So you would know a lot of scientists who have gone to the International Space Station right now who are not from the military. But in India, as of now, the earliest chances for going to space, as far as I see, will be from the military area. I hope that answered your question.
Thanks a lot, Avinash. The next question is by Mohan, and Mohan wants to know. Sorry, this has been addressed. So we move on to the next question, which is by Nakul for Ramya, and the question is, can I join ISRO after becoming a scientist? Ramya, are you there?
Yeah.
Okay.
Yes, I'm there. So can I join ISRO after is that the question? I'm sorry.
After becoming a scientist or astrophysicist, I guess is the question.
Yeah, you can definitely join ISRO along with before even you become a scientist or like having a career in astronomy, even if as an engineer or masters in electrical, electronics, mechanical, various fields, etc. If you are from an engineering background, you can join ISRO at even after your bachelor's level or master's level. And even after PhD, there is an opportunity for you to join ISRO for different space programs which they are conducting.
Thank you, Ramya. So there are a lot of similar questions in this section, and I have a general comment here that regarding the subjects that you should be studying if you want to pursue this as a career. People have already pointed out that maths and physics are very important, and in modern research and astronomy, coding is also a very essential skill. So focus on maths and physics and computer science, and then you can also do projects and try out. Also, there are a lot of open source astronomy projects. You can visit the Zooniverse page to see what kind of research you can directly get involved in as a citizen. So now we move on to the general Q&A. So there were a lot of questions. We are kind of overwhelmed here by the volume of good questions. We'll try and address as many as we can in this session, but if we are not able to answer your question, don't be disheartened. We'll try and get back to you. That's the reason we ask you for your email addresses. So going back to the daytime session, let's take a few questions from the daytime. The first one is from Debapriya Paul, and who wants to know what is the difference between sunspots and the coronal hole? And this is for Supriya.
Yeah, hi. That's a nice question. So basically, sunspots, it was explained before, are the magnetically concentrated regions that you see on the photosphere of the sun. So they look dark, like you might have seen in the pictures that were shown before, because of the huge magnetic fields that are on the sunspot. They are so strong that they won't let the heating happen from the layers that from below. Hence, they are relatively cooler than the surrounding surface. And the important thing is they are on the photosphere part of the sun. Coming to coronal holes, they are also relatively cooler regions on the coronal part of the sun, the outermost region of the sun. Basically, in these regions, the magnetic field lines stretch far out into space, much away from the sun, rather than looping back to the sun, which most of the magnetic fields do. So, because of this, most of the solar wind comes predominantly from these regions without being blocked by the magnetic fields that are present. So, these are the regions, coronal holes that are present in the outermost region of the sun, the corona.
Thank you, Supriya. The next question is from Abhishek Hiremat, who wants to know if we can shield solar flares by building some mega structures. Krishna, do you want to take that?
Yes. Hi. Hi, Abhishek. That's an interesting question. So, firstly, I presume here that what you want to ask is the massive particles. The solar flares are just massive increase in brightness. But the massive particles, because of coronal mass ejections or some of the ejections coming from the sun, that's what harms us. So I presume that you want to protect us from from these massive particles. So firstly, what are these megastructures made of? That's what something to ponder on. And then if we think of currently, Earth is already blocking some of the charged particles, right? Using its magnetic field. So maybe magnetic field is a way to block these charged particles. Whereas, of course, then with a magnet as giant as Earth, we are able to produce a very minute amount of magnetic field which can still block these charged particles. But if we want to block massive flares, maybe we need to build even a bigger magnet or something generate stronger magnetic field to prevent that. Yeah.
Thank you, Krishna. The next question is from Mohan, who wants to know how many times do we see aurora in a day? Soumya, can you take that?
Yeah. Hi, Mohan. It's a nice question. So, as you heard in the daytime session, and also as Prasanna explained during one of the Q&A sessions, auroras are basically natural phenomena which result from interaction of charged particles that are coming from the sun with the particles that are present in the magnetosphere of the Earth. So, these auroras occur in a region called auroral oval, and for this phenomenon to occur, first we need the particles from the sun to reach the Earth and interact with the magnetic field. So this is a continuous process which is happening all the time. So whenever the particles from the sun, in terms of in phenomena like solar wind or coronal mass ejections, are directed towards the Earth, whenever they manage to reach the Earth, they interact with the magnetic field and they produce these aurorae. So places which are closer to the North Pole, like Alaska or Iceland or some parts of Russia, you can see these aurorae almost every day. So I hope this is what you wanted to know. So I mean, we can see these auroras clearly in the night because they are faint compared to the light that we get from the sun. So if you are in a region which is closer to the polar regions of the Earth, then you see them frequently. And it also depends on the activity of the sun, how active the sun is at a given point of time. So when it is more active, when there are more sunspots, then there is a higher chance that there you see these auroras much brighter and they are much clearly visible in the night.
Thank you, Soumya. So now let's take a few questions from the nighttime section. So the first question in this category would be from Visual. I hope I'm pronouncing that right. The question is for Prashant, and the question is, where does the theory of general relativity break down?
Yeah, hi Vijwal. That's an interesting question and something to ponder about because we don't know much about what happens at the micro scales. So general relativity describes how space-time is affected in the presence of massive objects such as the Earth, Sun, or galaxies, or even applicable to the universe. But we don't know if this extends the other way around, that is towards the micro scales, the quantum scales. So particles at the quantum scales behave very differently compared to Earth or Sun or galaxies. So charged particles like the electron or neutrinos. Or even things which are smaller than that, like quarks. So we don't yet have a very good understanding of how general relativity is applicable to these particles. And it's very difficult to set up an experiment of this sort. So we believe that general relativity might not be applicable at these scales, but it is yet to be tested as of now. Yeah, thank you.
Thanks, Prashant, for the insightful answer. Next, we move on to a question by Ashwin Karthik, and this question is for Sandeep. Does every galaxy have a black hole at the center?
Yeah, so this is an interesting question. So actually, most of the galaxies are thought to have a massive black hole in the center, but not every galaxy have it. But it is like kind of observed, like our Milky Way galaxy has a massive central black hole, and similarly the Andromeda galaxy, which is our sister galaxy and having similar mass and similar size, that is also believed to have. But and so the problem is you cannot say, because the galaxies are very far away, and so in some galaxies the black holes are active, which erupts a lot of plasma, which goes to megaparsec very far away, and that is very, what we say, luminous, so we can observe it. So but all the galaxies doesn't have that kind of phenomena, and that's why we cannot say about the faraway galaxies if they are having black holes or not. I hope this answers.
Thank you, Sandeep. Let's take another one. This one is from Lochna. And this question is for Swagat. Why is the expansion of the universe accelerating? And what does this have to do with dark matter and dark energy?
Okay, this is a very good question, and it's related to a lot of other questions that a lot of other students have asked. So maybe this will answer a number of questions. First thing is, according to laws of gravity, if we put a lot of matter in the universe in a sort of homogeneous and isotropic way, in a smooth way, then the universe is either going to expand or going to contract. It's not going to stay static. Okay, so in general, universe would, depending on initially whether it started expanding or contracting, it could keep expanding or it could keep contracting. However, even though it has to do with Einstein's theory of gravity, it is very simple to understand in terms of a gas expanding inside some kind of a volume. In fact, the expansion of universe is very similar to a gas expanding. So if you have a gas inside a container and the container has a piston which can move, if the gas is hot and I leave the container, the gas is going to expand. As it's going to expand, it's going to cool down because it's transferring some of its energy to the piston's kinetic energy. So it will cool down and slow down slowly. So this is how we expect the universe to expand. So it should expand and slow down and slow down. However, what we see is that for most of its history, it was expanding and slowing down. But recently, about 4 to 5 billion years back, universe has started actually accelerating. So it's as if the piston was slowly moving, and then it started moving very fast. This can happen if the nature of the gas occupying the container changes. In the sense, if the nature of material in the universe changes, then this can happen. For most of the history of the universe was mostly dominated by light, radiation, and normal matter, electrons, protons, and stuff, and also dark matter. And these particles tend to slow down the expansion. However, recently, universe is now dominated by dark energy, which is a repulsive gravity. A repulsive gravity is also easy to understand in terms of a gas. Usually, when a gas expands, it cools down. But a dark energy gas, when it expands, it becomes hotter rather than colder. So it gains energy as it expands. So as this gas expands, it takes away energy from gravity, making the attractive nature of gravity weaker, thus making the expansion of the universe easier and easier as it expands. So it makes the universe accelerate and accelerate. In fact, one can actually test these things with such kind of gas in laboratory. The problem is we don't know any material which has this kind of repulsive or negative pressure. So it actually is accelerating because of dark energy, not because of dark matter.
Thanks a lot, Swagat, for the answer. The next question in this category is by Gauri Krishna, who wants to know how the sun is going to die. Very interesting question, very relevant for us as well. Mohan, can you answer that?
Yeah. So our sun is going to die as, it's going to have a planetary nebula, and its end stage is going to be a white dwarf, like how Arun had pointed out the Chandrasekhar limit. So the sun's final mass is below the Chandrasekhar limit, so it will still remain to be a white dwarf, and there will be a planetary nebula that is formed. The outer layers will be puffed out.
Thank you, Mohan. If I may add to that, so the white dwarf is essentially a dead star, which means that it's no longer fusing hydrogen or any other material in its core. And it's a very dense ball of gas. The density of a white dwarf would be, imagine the mass of the sun packed into something as small as the Earth. And so the density would be something like 1,000,000 to billion kgs per cubic meter. So it's a very dense ball of gas, and it's essentially a dead star. Okay, so we go back to the daytime section for the time being. This question is again for Mohan, and the question is, why is the temperature in sunspots lower than the surface temperature?
That's a nice question. So the sun is continuously radiating heat away into the vacuum of space, and this heat energy is replenished due to the nuclear fusion that's happening in the core and the convection that is happening in the convection zone. So you can see, like how Sajal had shown in his video, you have the bubbling of the gas that is happening. So what is happening is it is taking the heat from the interiors of the sun and it is throwing it out, and this heat is escaping into the vacuum of space. But in a sunspot, what happens? You have a magnetic flux tube which does not allow this plasma to flow out. So basically you have plasma which is frozen, it is not moving, and as the plasma is frozen, it radiates away its heat into space, and the heat is not being replenished by the interior layers. So that's why it cools down, but the surrounding region where the plasma can still have the convection, there, because the heat is being replenished, the temperature remains to be as it is. But in the sunspot, because the convection has been stopped by, or has been uh, obstructed by the magnetic field, you don't have the heat exchange happening, so it cools down and hence it's darker with respect to the surroundings.
Thanks, Mohan. Let's move on to the next one by Abhishek Hiremat, who wants to know, this question is for Rahul, and the question is, how much time does it take for light to basically reach the surface of the sun for the from the core, and why?
Hello. Uh, can you hear me?
Yeah.
Okay, so this question is from Abhishek. And the question, how much time does it take for the light from the core to the sun? Okay, I can see there are two similar questions. Okay, so before answering this question, we should understand the density of sun. So we know that the light from the photosphere from the surface of the sun takes roughly 8 minutes to reach the earth, but it takes around 100,000 years to travel from the core to the surface because of density. So the density of the core is of the order of 100 times the density of water. So you can imagine this dense of plasma is there. So when a photon interact with the atom, it directed in different directions. So due to this random motions, if you do some simple mathematics of Brownian motions and probability, then it turns out that a photon may take 100,000 years to reach the surface. So this is due to just Brownian motions and an interaction of photons with atoms. So I hope this is clear.
Thanks, Rahul. The next question is for Sajal by Rishwan, who wants to know, does the sun have any zones like the ozone hole in the earth?
Hi, Risman. It's a nice question. Actually, when we talk about the protective zone, like we have a living creature on the earth, right? So it is this ozone layer is protecting us from the radiation like X-ray or ultraviolet ray coming out from the sun. But for sun, as I explained before, that it has like a three internal structure, like centermost part is called core, and after this radiation zone, then convection zone. And the visible surface of the sun is called photosphere. And when we go to the atmosphere, it has two layers like chromosphere and corona. So that's all. So there is no like a protective zone like ozone layer in the earth atmosphere.
Thank you, Sajal. The next question is from Nakul, who's asked a very good question, which is why is the core of the sun so hot? And I can take this question. So the reason for the high temperature is essentially the pressure at the core of the sun. So the deeper, because of the layered structure of the sun, the deeper a layer, the more mass it has to support, right? So the core of the sun, because it's essentially holding up the entire mass of the entire weight of the sun, and as was pointed out earlier, there's a delicate balance between the gravity, which is trying to collapse the star, and you have the pressure, the gas pressure, which is keeping gravity at bay. And it's the balance between these two forces that keeps the star stable. And because the pressure is highest in the core, because it's supporting the entire weight of the star at the center, you have such high temperatures, and there is stratification of this pressure, which means as you go outward from the core, the pressure starts to drop. And it's the same reason why why the pressure, if you ever do deep sea diving, the pressure begins to increase as you go deeper and deeper into the ocean. And the reason is that deeper layers are supporting more weight from above. So that's the reason why the core is so hot. The next question is for Rahul, and it's from Lokesh, who wants to know how did we find out about the different layers of the sun?
Oh. Hello? Hello? Can you hear me?
Yeah, we can hear you.
Okay, so the question is from Lokesh. So how we found different layers of the sun. So as discussed previously in the talk, so we have generally classified our solar atmosphere in photosphere, chromosphere, and corona. So the idea to differentiate these layers is temperature. So we know that in photosphere, the temperature is around 6,000 Kelvin, and in chromosphere is around 10,000 Kelvin, and in corona it's 1 million Kelvin. So how do we find, because see, as temperature is different, so in different temperature, we see different ionization of atoms. So when we see these radiation coming from these atoms, the radiation, the wavelength is different. So using the wavelength that is coming from the ionized atoms can give you idea, okay, which part of the atmosphere is there. So generally, the visible light comes from photosphere, and the UV or EUV lights come from the corona. So just based on the idea of wavelength range, you can say. So we classify these photosphere, chromosphere, and corona.
Okay, thank you, Rahul. The next question is from Pehel, who wants to know why does this question is for Arun. Why does light turn from blue to red?
Hello.
Yeah.
Yes, I'm guessing this is in the context of Doppler effect. Right. So essentially, the idea is whenever you have a wave, it's not necessarily in the case of light waves. Whenever you have a wave, and when the source and the observer are in relative motion with each other, the wavelength of the wave that you receive will be different from the wavelength that is originally emitted by the source. A very dumbed down way of looking at it is if you're standing at the edge of an ocean on the beach, if you're moving towards the water, the number of waves you'll count every minute will be higher compared to when you're standing still. So the frequency increases. So similarly, if you are, as an observer, you're going towards the source, the frequency increases, so the wavelength decreases. So this tells you, and the rate at which this frequency increases, or the amount of the frequency increase or decrease, will tell you how fast you're moving relative to the observer. So if you're moving away from each other, your frequency decreases, and if you're moving towards each other, the frequency increases. That in effect tells you whether, in this case, light is getting blue shifted or red shifted. That is, if the frequency is increasing or decreasing.
Thank you, Arun. The next question is for Samuel. This question is from Lokesh Malik, who wants to know which galaxy is going to collide with the Milky Way.
Thanks, Shivam, for forwarding the question. And hi, Lokesh. It's an interesting question. So my first response is you shouldn't be worried about this. In fact, we shouldn't be worried. All shouldn't be worried about this because even if something like that is going to happen, it's going to happen over a time which is of the scale of billion years. Now, what can happen is in our local group of galaxies, we have these two massive galaxies, which is our own galaxy and Andromeda galaxy, which is again a nearby spiral galaxy. And recent studies of the proper motion suggests that our galaxy and the Andromeda galaxy, or M31, can collide after about 4 billion years. Now, these things are predictions are highly dependent on how precise the measurements of the velocities of the galaxies are in space. And since they are distant objects, for example, the Andromeda, they're distant objects, so it takes a lot of time, or maybe 5 to 10 years to record their space velocity. And then you need mathematical modeling to predict what is going to happen, or understand where the galaxy was before at certain point of time. And there is another galaxy which is close to our galaxy called the Large Magellanic Cloud. And if the proper motion results and the modeling has to be believed, it's possible that the Large Magellanic Cloud can collide with the Milky Way in about 2 to 2.5 billion years. So I hope that answers your question. Thank you.
Thank you, Samuel. The next question is for Varun by Nirmiti Deshmukh, who wants to know what is the difference between a reflector and a refractor telescope.
Yeah, hi Nirmiti, very nice question. So basically reflector telescope uses mirror to image the distant object, whereas the refractor uses lenses to image those objects. And over the globe, the scientific telescopes which are used are usually using the reflectors, not the refractors. I hope this answers your question.
Thank you, Vanu. We can take a final question. The question is, what was there? So Swagat, this is for you. What was there before the Big Bang, and is it related to the multiverse?
Okay, this is a little different question. Okay, I want to clear certain concept which is usually there in popular culture of science, which is different from what we understand as scientists as Big Bang. So the Big Bang, the word Big Bang could have two meanings. The first meaning would be the Big Bang theory, which we talk about. In this Big Bang theory, there is no bang. This Big Bang theory says that as we go back in time, universe was denser and hotter. In fact, if we go back almost about 13.8 billion years, universe was so hot and dense that it was in a plasma form, like our sun. So universe expanded from this plasma form to form the present cold galaxy dominated universe. This is the Big Bang theory. Now there is a theoretical extrapolation of this theory that if we go back even further in time, then when the energy of the universe was very, very high, there's a particular energy, it's called Planck energy. Around that time, as we reach, these laws that we are using, this theory of gravity which we are using to understand the universe at the early times would actually break down, and we do not know what would happen. But if we naively trust our theory, then it seems like at a time in the past, the density and the temperature of the universe was infinite. And this is termed in physics as a Big Bang singularity. So I think in popular culture, people think by Big Bang, they think of this singularity, and they think that the universe started at the singularity. But as scientists, we do not know about it, and we have no idea what happened during singularity. So it's possible that universe existed before it, and it was contracting and then expanded back, or it was static for a long time, then expanded back. These are all the possible theories. And whatever is multiverse is definitely after this Big Bang singularity, but before the hot Big Bang phase. So the multiverse has to do with initial expansion called a very accelerated expansion called cosmic inflation, which creates patches of universes here and there, just like a lot of islands separated by water. So that is definitely after this singularity Big Bang, but before the hot dense plasma phase that we have in our universe.
Thank you, Swagat. If I may add, my understanding is that the conception of time begins at the Big Bang. So what existed before the Big Bang is something that we are actually not equipped to address at this point, because if time did not exist, then the conception of before and after also does not exist. Okay,
yes, if you trust the classical theory. Yeah.
Okay, Prasanna, can you take over for the concluding remarks?
All right, so thank you everyone for attending today's session. Thanks for your time and interest. We received a lot of questions. Whatever we answered is just part of it. And we will make an effort to respond to most of these questions through our website, which is listed on the screen. So what you can do is visit this website and see if your question is there. Go through the frequently asked questions section, which we keep on updating as and when we get new questions. And if you have any further questions, we have made provision of the form to ask questions via that website. If you have any other queries, if you want to get in touch with us, askastronomer@gmail.com is the email address. So please ask your questions, any queries on this email address. So we had this as a one-time session. So here onwards, if you have any further interest or specific queries, we'll be happy to help you. So yeah, on behalf of our entire team and all the participants, I would like to thank everyone, both hosts as well as participants, to be part of this Ask an Astronomer session. We call it as Let's Talk Astronomy. So yeah, thank you everyone. Have a good day.